Good afternoon, class. We are looking at section 4.2, how derivatives affect the shape of a graph. We are going to finish what we started. In essence, we've done the first half. We're going to go through the second half. We covered maximum and minimum values. Now we're going to go over how derivatives affect the shape of a graph. Differentiation formulas. Various formulas, delta y versus dy, linearization, which is in essence finding the tangent line. Max and mean, their formal definition, and also if you happen to have an extreme value theorem concept, which means if you happen to have a closed interval and a continuous function, the process of finding absolute max and mean is by finding f prime equals 0 or it doesn't exist. In other words, the critical points, and then evaluate the function at the endpoints as well as the critical points. The largest value will be an absolute max, the smallest will be an absolute mean. Here's the summary of the section. A function is increasing, obviously, when f prime is positive, decreasing when it's negative. A critical point is where f prime is 0 or doesn't exist. A relative extremum refers to a critical point at the top or bottom of an interval. A function is concave up where f double prime is positive, concave down when it's negative. When concavity changes, it gives rise to an IP or inflection point. If a function is concave up, the graph lies above all its tangent line, and if it's concave down, it's below the tangent lines. In order to graph, we use the information from prior knowledge of mathematics in algebra, pre-calculus. We also add calculus to find relative extrema, intervals of increasing, decreasing. That's using f prime. And then using f double prime with the sine graph, we find where the function is concave up, where the function is concave down, as well as point or points of inflection. The first derivative test indicates if the function is increasing first, then it's decreasing. As it changes from increasing to decreasing, gives rise to a local max. On the other hand, if it's decreasing first, then it's increasing, it gives rise to a local mean. And it is the sine graph that gives us the information. Test of concavity. Basically, the function is concave up when f double prime is positive and concave down when it's negative. And when the change happens is a point of inflection or an inflection point. So in short, a function is concave up when f double prime is positive and concave down when f double prime is negative, which is different than the second derivative test, and we don't want to mix them up. The second derivative test gives you half of the information of the first derivative test. The CPs, the critical points that we found when we set f prime equals 0 doesn't exist, we evaluate the second derivative at that. If it's negative, the graph is concave down in that vicinity, which means that must be a local max. On the other hand, if this value is positive, that means graph must be concave up in that vicinity, and that means it must be a local mean. We discussed the end behavior of a polynomial, and it basically depends on the first term, the leading term. If the power is even, it will look like either f of x equals x squared or f of x equals minus x squared, depending upon whether a sub n is positive or negative, the leading coefficient. On the other hand, if you're dealing with odd powers, it will look like either f of x equals x cubed or minus x cubed. Again, depends whether a sub n is positive or negative. We also have behavior here, an x-intercept, which depends on the multiplicity of a zero. M is the multiplicity of the zero. If it's odd, the graph crosses the x-axis at that point. If it's even, it can't, it will bounce back, as you can see in these examples. We graphed this using prior knowledge of mathematics. Then we added information from calculus, so the graph became more detailed. First, we found CPs. We did the first derivative test, and we found where the function is increasing, where the function is decreasing. We found local max as well as local mean. I did the second derivative test, and I'm going to emphasize again and again. You don't want to use that for graphs, but it's a wonderful tool for applications because you don't have to do the sign graph. So it gave us half of the information we had in the previous page. We also did try to find the inflection points using the test of concavity. Y double prime or F double prime, we set it equal to 0. We use the sign graph to find where the function is concave up, concave down, if we have an inflection point. And we put all the information together, first using a table, a summary table. And of course, the information from the end behavior of the function. And we graph this. So this is what we have done so far. We're going to go to new stuff, and we are going to graph f of x equals half of x to the power of 4 minus x squared. So using prior knowledge of mathematics, I need the intercepts. So I'm going to set this equal to 0. And to do that, I'm going to factor either x squared or half of x squared, because I want to set this equal to 0. This gives me x equals 0. And the multiplicity is 2. This gives me x squared equals 2. X is plus minus square root of 2. Each one has a multiplicity 1. This is the only one with multiplicity 2, okay? It so happened to be the y-intercept as well. 0, 0 is both x as well as y-intercept. So if I were to graph this, let me use a different color. 0, 0. And square root of 2 is about 1.41. So roughly here, 1.41 or square root of 2 comma 0. This is negative 1.41 or negative square root of 2 comma 0. And if I look at this one, n is a 4 and a sub n or a sub 4 equals 1/2, which is positive. So this is my n behavior looking like an x squared. Finally, if I look at this one and remember that it has multiplicity 2 at 0, 0, it can't cross, and I use double arrow to mention that this is a place where it can't cross. So without the knowledge of calculus, if I were to graph this, it will cross the first x-intercept, but it has to come back at some point. and I may not know at what point. But it can't cross this second one, right? At 0, 0. So it goes down and it has to come back up again. And here's the graph. Now, one thing that helps with graphing, prior knowledge of mathematics, is to know f of minus x equals f of x, which makes this an even function, which makes it symmetric with respect to the y-axis. So the right half and the left half are identical, are symmetric with respect to the y-axis. So we should know that. So we're done with the graph using prior knowledge of mathematics. But what we want to do, we want to make it more precise by using calculus. Again, this we could have done without knowing any calculus. And we have the intercepts, we have the end behavior, we have the fact that at 0, 0, it can't cross, and it looks, and it's an even function, so it looks pretty good. Let's erase everything and go through the process of finding f prime half times 4 is 2x cubed with the minus 2x, because I want to use the first derivative test. And I need to set this equal to 0, and to do so, I have to factor this expression. So let me take out the 2x. And x squared minus 1 is x plus 1, x minus 1. So that gives me 3 answers when I set this equal to 0. X equals 0, x equals negative 1, x equals positive 1. So there are 3 zeros for f prime. That means those are CPs, critical points. To do the sign graph, we go from negative to positive infinity. At negative 1 is 0, at 0 is 0, at 1 is 0. The numbers at the bottom represent the x value, and they must be in order. Now, one thing I mentioned last time, I'm going to mention it again. Because this one, each one has exponent odd, or you might say 1, 2, 3 separate answers, and it's of degree 3, they will alternate. So 2 ways to approach it. The exponent for each one is odd. Doesn't have to be even odd. 1, any odd number will do. The other one is easier to see. This is degree 3. There are 3 answers, so nothing repeats. So whatever I find, the rest of them alternate. But if I were to pick a TP, short for test point, TP short for test point, negative 2 here, negative 1/2 here, 1/2 here, and 2 here. For example, if I put the negative 2 here, becomes negative. Over here, negative 2 plus 1, negative. Negative 2 minus 1, negative. Negative times negative times negative. The first entity is negative, and then they alternate. But if you have any doubts, pick another one. For example, if I pick negative 1/2, this is negative. With plus 1 becomes positive. Negative 1/2 and minus 1 is negative. So negative times positive makes it this positive. Meaning, yes, they do alternate. And you have a choice of going through that, but understanding why it alternates. So what does it mean? Well, it's wherever it's negative is decreasing. So from negative infinity to negative 1, union 0 to 1 is decreasing. Let me just throw in the arrows. They see arrow down, arrow up. So decreasing here, increasing here, increasing here. So that's decreasing from negative infinity to negative 1, union 0 to 1. It's increasing from negative 1 to 0, union 1 to infinity. And we need to find the local max and local min. Well, decreasing changes to increasing. This is a local mean. Increasing to decreasing, local max. Decreasing to increasing, local mean. All those 3 values, we have to evaluate the function added. Because they are both of even degrees, plus and minus 1, they give us the same number, everybody. So this to the power of 4 is positive, doesn't matter positive or negative. This to the power of 2 is positive 1. So it results in 1/2 times positive 1 minus positive 1, which makes it negative 1/2. Therefore, local minimum is equal to negative 1/2 at plus minus 1, and that means the following pairs. 0 is easy, class. If I put it into the original function, obviously becomes 0. So local max equal to 0 at 0, 0. And as I mentioned, increasing wherever you see positive, from -1 to 0, union 1 to infinity, decreasing wherever you see negative sign, negative infinity to -1, union 0 to 1. So the first derivative test gives us a lot of information, everybody. We want to move on to the next step, which is finding inflection point. So we're going to move on because we don't have enough room here. We're going to move on to the next page, and we are going to write the function, its derivative, and the information we got: intercepts, minimum, where the function is increasing, where the function is decreasing. 0, 0 is an x-intercept. It is also y-intercept. It is also the location of the max. So this is the information from the previous page. So what is f double prime? 6x squared minus 2. Since I want to set this equal to 0 and solve, I'm going to take the 2 out, factor the 2 out. And so I get 3x squared minus 1 is 0. Three x squared equals 1. And x squared equals 1/3. So it makes x plus minus the square root of that, which is plus minus 1 over square root of 3. And we are going to do the sign graph for f double prime. All right. So we need, again, this is x at x equals -1 over square root of 3. F double prime is 0. The same thing as 1 over square root of 3. We need to take a test point. And by the way, before even we move on, f double prime is of degree 2. And it has 2 solutions, so they will alternate. Or when we say 3x squared minus 1, if you want to factor it, of course, we then factor it, you will end up with 2 factors. So, and each one is odd, meaning the exponent is 1. But stick with the fact that you have 2 degree 2 with 2 answers, so they will alternate. What are the TPs or test points? So if I want to use TPs, the easiest one would be 0 in between, right? And to the left of -1 over square root of 3. Square root of 3 is 1.71 roughly. So minus 1 over that is less than, is larger than -1. So I can use -1 here. I can use +1 here. Okay. And so I'm going to stick with 0. If I put 0 into f double prime, this goes to 0. The answer is minus. And as I said, they will alternate. But if you have any doubts, put -1 here. Makes it +1 times 6 is +6 minus 2 is +4. And the same thing with 1. Now that we have that, it means that the function is concave down here between the two, concave up from -infinity to -1 over square root of -1 over square root of 3 union 1 over square root of 3 to infinity. So that's the meaning of this. Furthermore, we have two IPs or inflection points. At what point? These are the x coordinates. So plug it into the original function to find the y coordinates. And to do so, whether I put positive or negative makes no difference, because remember, this is a even function. Both of them have a degree even, and whether you have a negative or positive, it gives you the same. So first and foremost, I hope you realize if you raise this to the second power, it becomes positive regardless. So 1 over 3. And since this is the power of 4, 1 over 3 squared, or 1 over 9. So this is 1/3, this is 1 over 9. Let me erase them, it makes it easier. This is 1 over 18, and this is minus 6 over 18, because we are taking common denominators. And so we have the IPs, we have two of them at plus minus 1 over square root of 3 and minus 5 over 18. And I'm changing them to decimal notation, therefore I can show the result on the graph. That's the reason. So, and you can, when you write plus minus 1 over square root of 3 and minus 5 over 18, that represents two different pairs, everybody. Two different pairs on rectangular coordinate system. Let's write the summary table, x and y. So we are going to write these pairs. We're going to write these pairs, all of them in a summary table, and we're going to follow that. So starting with the x-intercept, plus minus square root of 2 comma 0. Let's just make sure we understand this is 1, this is 2, negative 1, negative 2, this is negative 1, this is 1. So we want minus 1.410. So somewhere between negative 1 and 2, closer to negative 1. And that's the first point. The second one, positive 1.41, positive 1.41, between 1 and 2, closer to 1. Okay, so those are the x-intercepts. The other x-intercept 0, 0 is also the y-intercept, is also the max. So this is 0, 0. Because it's the max, we draw a double arrow, meaning it can't cross it when it hits that. So when it hits that, it bounces back. Now IP, I'm changing 1 over square root of 3 to 0.6 roughly. So minus 0.6 and minus, let's say, 0.3. So here, this is negative 1 minus 0.6 is somewhere between these two numbers, closest to negative 1. And minus 0.3, it's somewhere between these two numbers, closest to 0, right? And so we get somewhere here, okay? And now positive 0.6 and negative 0.3 gives us that. So those are the two IPs. We have the minimum at negative 1 half. So this is negative 1. And this is negative 1 half, right between 0 and 1. And then positive 1 and negative 1 half. However, let me do the double arrow for this one because it's the minimum. And this one, positive 1 and negative 1 half, and do the double arrow also. And go back to this. The degree is 4. A sub n is positive. The first and the fourth quadrant, you do need that n behavior for the sake of the graph. So here and here. So as it comes down, it hits the first x-intercept, then this point, and it has to come back up. This point continues. This point has to come back down. It can't cross this point. And then this point has to come back up, and it crosses this x-axis. It's very straightforward, everybody. So we combine the information from here, meaning calculus, as well as prior knowledge of mathematics. The number of bacteria in millions present in a culture at time t in hours is given by n of t equals 2t times 5 minus t squared plus 14t plus 100. Find the initial population. Simply put, elementary algebra replace the t with 0. When we do that, this goes to 0, this goes to 0. The only answer is 100 million bacteria, initial population. At what time before 10 hours will the population be maximized? Before 10 hours means minus infinity to 10. However, because this is time, we can't go negative. 0 to 10. 0 is included, but 10 is not because it says before, and I want to multiply this to get 10t minus 2t cubed. So for the next step, which is differentiation. So I'm going to write the function as such, and the interval is half closed, half open. Again, before 10 means negative infinity to 10. But it's time, therefore, from 0 to 10. And before 10 means 10 is not included. Half closed, half open. So we differentiate. N prime is minus 6t squared plus 24. Since we want to set this equal to 0 and solve, I am going to factor the negative 6 out. And t squared minus 4 is t plus 2, t minus 2. That results in two answers. When we set them equal to 0, we get plus minus 2. Which one of them we can use? Can we use both of them? We look at a given interval, and we can only use t equals 2. It's time. We are going to do the first derivative test. I want to show you something first. We are going, normally we go from minus infinity to infinity, but this is 0 and this stops at 10. And you can use test points. For example, over here we can use 1, over here we can use 5. Even if you use 0, that's fine as a test point. So if you put it into n prime, 0 will give you positive 24, that's positive. If you put 1, minus 6 and 24 is positive. So this is positive, and it alternates because they were both, anyways. There was degree 2 and there were two answers, but we used one of them. But if you have doubts, put, let's say, any number you want to the right of to. For example, 5. It becomes 25 times minus 6 plus 24 is a negative value. So what it means is, let me throw in the arrows. Because it's increasing and then decreasing, the maximum occurs at t equals 2. This is, of course, local max according to the first derivative test. However, because it's the only critical point and it's half closed, half open, this is also an absolute max. What I want to show you is the second derivative test does the same thing, and it's a tad faster. You don't have to go through the sine graph. So take a look at n prime. What is n double prime, everybody? Minus 12t. Now, according to the second derivative test, you have to plug in the CP. It's either positive or negative. So if I plug in 2, I get minus 24, which is negative. Negative If the second derivative is negative, that means concave down. That means maximum. So negative means concave down, which looks like this in that vicinity. So the maximum occurs at that. That's why for applications, I believe this is a tad easier to find the maximum population. Put this number t equals to into the original function or the one we found. Makes no difference whatsoever. The first one, actually, the original one is a tad easier because I hope you realize this is 4. So this becomes 1. 2 times 2 times 1 is 4 plus 28, 32, and 100. 132. What? 132 million bacteria. We want to sketch the graph of f of x equals x minus 2 to the power of 2/3 plus 1. I hope you remember we have worked on this when we were finding maximum and minimum, absolute max and min. So I want to show you how to graph this using prior knowledge of mathematics. So I'm going to rewrite this as the same thing, which means cube root to the power of 2 plus 1. So going from here to here is elementary algebra. So if I want to graph this, I'm going to use one of the elementary functions, and that elementary function would be cube root of x. And you remember the cube root of x looks like this. Domain and range are all real numbers. Next, I'm going to use cube root of x minus 2, which means I am going to move this graph to the right by 2. So move it. So to the right by 2 units. Move it to the right by 2 units. The next one is to square the function. So what happens when you square it? When you have a function, for example, this function, everybody, okay? When you square it, this portion which is above the x-axis and this portion which is above the x-axis is positive and it gets squared up. For the portion which is below the x-axis, this portion, as you recall, it flips over and gets squared up. Okay, therefore, this portion is positive, just gets squared up. This portion, when it gets squared up, flips over and becomes positive as well. Reminding you of what we learned in college algebra, pre-calculus. Finally, we are going to add 1, which means this green function, we move it up by 1. So move it up by 1. So originally we have the red one. We move it to the right by 2, we get the blue one. Since we square this, notice the blue one on the positive side gets larger because it gets squared up. And the one below the x-axis gets squared up, becomes positive. And then this plus 1, look at the green one, goes up by 1 unit. All right, let me erase the mess so we can continue with calculus. So what we need to do is to differentiate this. And to differentiate this, because we want to use the first derivative test, everybody. To differentiate this, I'm going to use this one, not that one. 2/3 times x minus 2 to the power of 2/3 minus 1 which makes it negative 1/3 times the derivative of the inside, which is 1. So we simply differentiate this expression. Okay. I'm going to rewrite this by taking this down, making it positive 1/3 or a cube root. F prime equals 0. A fraction is 0 when the top is 0, and that doesn't produce any solution because the top is a number. F prime does not exist or it's undefined. A fraction does not exist or it's undefined when the bottom or the denominator is 0, and that would be x equals 2. So we do have a critical point at x equals 2. So we are going to do the sine graph for the first derivative test, everybody. So from negative infinity to positive infinity at x equals 2, f prime dne does not exist. So we use TP to the left of 2, we can use 1. To the right of 2, we can use 3. So we can, well, 0 is even easier, and 3 here. So if you plug in, let's say 0 into f prime, this format or that format, if you put it in here, notice 0 makes this negative. Cube root of a negative is negative. And positive over negative is negative. The first one is negative and it alternates. If you have any doubts about alternating, plug in 3. That gives you positive 1. Cube root of positive 1 is positive. Everything becomes positive, which means we have local minimum at, let me just throw in the arrows. See, arrow down, arrow up. So decreasing here, increasing here. At 2, we have a minimum. And it's very easy to calculate the original function at 2. If you go back to the original function, if you plug in 2, this becomes 0. So the answer is 1. So the local minimum equals 1 at 2, 1. How did we get that? Put the 2 into the original function. This goes to 0 or this goes to 0. The answer is 1. Where is the function decreasing from negative infinity to 2? Where is it increasing? From 2 to infinity. So we no local max, by the way. So we write that increasing and decreasing portion. We are going to go with f double prime. In order to get to inflection points. And to differentiate that, we are going to use this one, 2/3 times negative 1/3. So f double prime would be 2/3 times negative 1/3 x minus 2 to the power of negative 1/3 minus 1, and then the derivative of the inside is 1. So let me just clean this up. This was minus 1. Therefore, we get minus 2 over 9, x minus 2 to the power of minus 4/3, and we take this down, make it positive 4/3, and into a cube root. Now, you really don't need to do the sine graph on this class. I'm going to show you, but if you want to do it, that's fine. We'll do it both. The reason you don't have to do a sine graph, this expression is always negative except at 2. First of all, at x equals 2, this becomes 0 and it becomes undefined or does not exist. What happens at any other number, regardless of positive or negative? Cube root of negative is negative, cube root of positive is positive, regardless, because this exponent is 4, an even number, whatever the number to the power of even becomes positive, times 9 is positive. Because the numerator is negative, it is always negative, except at x equals 2. So right away, it's always concave down. How do you write always concave down when x can't be 2? You would write it's concave down from negative infinity to 2, union 2 to infinity. That's how you write. And you're done. But just in case, if you insist to do the sign graph on that, this function f double prime is 0, never, because the top is a number. It doesn't matter positive or negative, large or small. F double prime doesn't exist when the bottom is 0 or x is 2. And if you do the sign graph on that, to the left of 2, an easy point would be 0. If you plug in 0 here, okay, becomes negative. Cube root is negative. The power of 4 is positive. Times 9 is positive. Negative over that makes it negative. If you pick a number to the right of 2, everything becomes positive at the bottom. The top makes the whole thing negative. So we get the same answer that was mentioned here. Do you have to do that? Absolutely not, but I just wanted to show you in case. All right, let's go to the next page and try to graph this. First, we are going to write all the information we found. Here's the function in 2 different formats. Here's where the function is increasing, decreasing, concave down, and the minimum is at 2, 1. The thing we didn't do in the previous page was to find intercepts, and that's what we are going to do. First, the y-intercept is very easy. If I replace the x with 0 here or here, makes no difference. Okay. 0 gives me -2. When I square it, gives me 4. Cube root of 4 plus 1 precisely. And for the sake of graph, I'm going to put it with decimal, almost 2.6, because when we want to graph it, it makes it easy. So again, replace the x with 0. This gives you cube root of 4 plus 1. There is no x-intercept. Why is that? Because you have to set this one equal to 0 and solve. So let's set this one equal to 0 and solve. Let's see why this is the case. Move the 1, becomes -1. Now, remember the index is the denominator. That's why anytime you have a case like that, your first step from here on is to raise it to the power of the denominator. So if I raise both sides, to the power of 3, the left side becomes x minus 2 quantity squared, and the right side becomes -1 cubed. Now, x minus 2 squared, because of this, it's always positive with the exception of x equals 2. And this one is always negative, therefore there is no solution. Now, what do? We want to sketch the graph. So we are going to plot some other points. And so what I'm going to do is I'm going to write a summary of what we have, everybody, and take it from there. So we have this pair, or 0, 2.6. We have this pair minimum 2, 1. But it's at this point helpful to pick up a few more points. And we're going to get easy points. First, points that they don't need a calculator. So if, for example, if I pick 1, I get -2. 1 minus 2 is -1. Cube root is -1 squared. +1 and 1 is 2. So 1 gives me 2. Let me pick another easy point, 3. 3 minus 2 1. Cube root of it is 1. Square root is 1. 1 and 1 is 2. 3 comma 2. And that may be enough, but just to give you an idea, because it's a cube root, let's make it, for example, minus 8. So if you choose minus 6, makes it minus 8. Cube root is minus 2. Square root is 4, and 1 is 5. Make it 8. 10 minus 2, right? If you choose 10, 8 cube root is 2, 2 squared is 4, plus 1 is 5. So those are easy points. And on purpose, I picked something that you have to use a calculator, everybody. Okay, you have to use a calculator. I did that on purpose. So let's plug in the numbers. This one, I'm going to use 2.6. Okay, so 0, 2.6, somewhere between 0 and 5, and a tad closer to 5. That's the first one. 1 comma 2. So 1, 2, 3, 4, 5. So this is 1, and this is 2. 2 comma 1. 2, 1. So it's here. It's here. Okay. 2 comma 1. 3 comma 2. So 1, 2, 3. Go up by 2. It's there. Negative 1. 3.08 is almost 3, a little bit above that. Minus 6, 5. So this is minus 5. This is minus 6. And this is 5 up here. And 10. This is 10, 5. So here. Put them together. And that's your graph, everybody. That's your graph. What do we notice? Besides the points that we put in, this is the minimum value 2, 1. Not only this is a local mean, it's also an absolute mean. It's decreasing from negative infinity to 2. And it's increasing from 2 to infinity. It's concave down from negative infinity to 2, union 2 to infinity. Everything that we have found, it works here.